So I will talk about the photometric follow-up of the space-based transit missions or transit detections, showing here the experiences that we've gained from Corot and what we hope to apply then also for Plato. And some of these motivations, which I show you, were already mentioned by Anna, but I will maybe show them with a bit more detail also. So let's share the screen. Let's see, share the screen should be the PowerPoint here. Share. Okay. You see now the presentation well?
Yeah.
Yeah.
Okay, cool. Good. Yeah. So this is to some extent based on a talk that I gave about 4 years ago in a workshop for advanced amateurs in Kea in Greece. And yeah, as I said, it's based on a lot of the examples and things I given are from Corot still, but these basics haven't changed at all. So here, special thanks to the team that worked on this about 10 years ago. So why should we do photometric follow-up of transits detected from space? And there are two main motivations. The one is to find false alarms in planet candidates, and the other one is to follow up confirmed systems, confirmed transiting planets, with several motivations, which we go through parameters here. So on the first one, the detection of false alarms in planet candidates, most space missions, and I'll show a table in a moment, I think all except Kepler really, have this issue that the spatial resolution of the telescopes of the space missions is rather poor. In Corot, which I show here in the upper image, actually the pixels are relatively small. They are 2.3 arc seconds, but they had defocused the image. And in other missions like TESS and Plato, the pixels are actually quite big. So a TESS or Plato pixel will be about like 5 to 6 of these pixels, so in linear direction, so over 20 of the Corot pixels. So what we see here is that the target star, the one we think we are observing, and Corot had a photometric aperture that was adapted to the given stellar field. But it doesn't matter much if we look at single large pixels or through a large photometric aperture. The situation is the same within this fairly large area. We observe something on the space mission, a little transit, but we hope it's coming from the target star, but it might also come from some of these other stars, which are here, there's crosses, which are the cataloged stars, and it might even come from other stars which are not in the catalogs. So that's why we do the count-based observations, which we see down here. We see an image from the ISC 80 telescope, which is an 80 centimeter telescope in Tenerife. And we see, of course, it has a much higher spatial resolution. Spatial resolution from ground is more or less 1 arc second, or sometimes even better, and quite often a bit worse, versus the 15 to 20 arc seconds that are common to these 3 space missions, Corot, TESS, and Plato. But of course, we have a much poorer photometric precision from ground in general. So how can we do something useful with that? Doing ground-based observations. Does that not advance? Yeah, first here a comparison of the various space missions. Just looking at the pixel size, Plato has 15 arc seconds, TESS has 21 arc second large pixels. Corot had smaller ones, but a point spread function that was very large. And only Kepler really had a higher spatial resolution. And indeed, in Kepler, the photometric follow-up was not really very needed or relevant. So, eclipses from space versus eclipses from ground. The main point is, in Corot, we observe a faint signal, or in some other space missions, a faint signal on the flux from the space-based instrument. It's very faint, very shallow. Now, if this comes from and there can be now several possibilities if you observe it. It might come indeed, that signal which we observed in space might indeed come from the, if we here look at the higher resolution image, might indeed come from the target, and it will be another very shallow signal, more or less similarly shallow, if the, at least if the flux of the target dominates in the photometric aperture of the space mission. It will be more or less that Ft over T will be more or less the same than Fs over, the delta Fs over Fs. They will be more or less the same. They will be shallow. But if the transit we observed here comes from one of these fainter stars around, in order to generate that transit from a faint source, the eclipse on the faint source has to be deeper, much deeper. And it depends how deep it has to be, depends on the faintness of the nearby star. If it's very faint, the eclipse has to be very deep, and there's then of course a faintness limit because eclipses can't be deeper than 100% and typically of the flux. Typically, they are not deeper than 50% of the flux of a star, which is an eclipsing binary where both components have more or less the same size and occult each other. So there's a faintness limit that we can also set. But anyway, we may have here 3 stars, which could, this one is fainter, so it has deeper eclipses, which are potential targets, potential eclipsing binaries. And we have to find out which ones they are. And so if we do our photometric follow-up observation and we can detect the transit on the target, yes, this is nice. This is an on-target transit then in the space data. But of course, if this one is correct, we have what we call a contaminating eclipsing binary, which is an eclipsing binary nearby to the target star that contaminates the flux of the target star. Oops, sorry. And it could be any of the other ones. So we have different potential outcomes from an observation of a photometric follow-up. We may have an eclipse on the target, and this is nice, and we know the transit is on the target. We may detect an eclipse on a contaminant, and then we also are certain that we have a contaminating eclipsing binary. These cases are closed. And then something that happens quite often is that we don't detect anything in the photometric follow-up. But we may still use these data, and we have done that quite often when we did the cohort follow-up. There are 2 requirements. We have to make 2 questions. With our photometric position, which we can estimate, which from our data set, would eclipses of the expected depth be detected on each of the contaminants? For example, there are 3 or 4 contaminants. Could we, and we can calculate how deep the eclipses have to be in order to generate the signal in the space data. So would we have expected these definitely or not? That's a question. And the other question is, are we certain to really have observed at the time of the transit? Have we observed at the correct time? Are we certain, if we observe these few hours in this night, that there must have been a transit or an eclipse? And only if we can answer yes to these 2 questions, and we don't see an eclipse or anything in our data, then we can really conclude that the transit cannot be on any of the nearby contaminants, hence it has to be on the target. And on the target, we can't detect it because, for example, in the space mission, it was only an 0.1% deep transit. And that is something that we simply can't see in our photometric count-based data. Else, if we have to say no to one of these 2 questions, then the data are indeed inconclusive. So important here is for this indirect conclusion that the absence of deep eclipses on contaminants indicates the absence of contaminating eclipsing binaries. We have to be certain that we observe correctly. And for that, we need then, and that is where ETD comes in also, that we need to have reliable ephemeris. And we also have to have reliable errors on these ephemeris because we may have ephemeris that tell us nicely that this night there will be a transit, but maybe the error of the ephemeris is already plus minus 5 hours. And then we can easily lose that transit. So we cannot conclude then anything from non-detections. We can still attempt to do these observations then to see maybe we can catch an eclipse of either the target or of the contaminating or of the nearby stars. But if we don't see anything, it's not conclusive. Okay, that is our, I think, the main motivation for our efforts with the ground-based follow-up. Then another motivation, and there has been talked by Simone, the second talk, is the follow-up of known planet systems, where this has been mentioned already, that we may detect transit timing or period variations or eclipse timing variations. And these can be used either for both the detection of non-transiting planets in a system with known planets and for the mass determination of planets. This has been shown here in Kepler data purely already quite a while ago, that they, from transit timing variations or period variations, they derive that there's a third planet in Kepler 159. These are it's a so-called O-C diagram where the observed timings relative to predicted timings are shown from using a linear ephemeris. Other work that was done on that, which was follow-up work on Kepler detections, was done within the so-called COINET collaboration, where we worked a few years ago on, where they here have the timings from the Kepler data that go up to 2013, and then Kepler basically discontinued. And they reobserved two planets in the Kepler 9 system, Kepler 9b and c, several times, and then they could set better limits to the densities using the mutual interactions between these planets from predictions, orbital predictions. I also predicted that Kepler C will stop transit. And here another example that they did on Kepler 82. There were also two planets which had known transit timing variations from Kepler again until 2013, where they observed again later in 2018, 2017, and they could derive that there must be another non-transiting planet with about 21 Earth masses. Another point that has been mentioned by EFA has been the maintenance of the ephemeris beyond the end of a space mission. This was something that was very serious with Corot, because the Corot had observations that were only maximums 5 months long, and then the uncertainties of the ephemeris started to add up. And what we plotted here is of the different Corot planets which were observed between 2007 and about 2012. You see the timing uncertainty. It first starts flat, which is basically during the Corot observation, and then this error goes up. And it depends on typically on the depth of the transits and on the brightness of the target system, how steep this uncertainty goes up. The issue is there are quite a number of planets where the timing uncertainty may get larger than 2 or 3 hours already a few years later. And these are then planets you can't really reobserve from ground again, because you are not certain even if in a given night you can observe and transit or not. That's why we made a reobserving campaign of most of these planets, and many of them are also in ETD from amateurs mostly. Then 2 papers that Stephanie Ratz and a group led by me wrote or published follow-up observations. And then Peter Klagewig last year added also the test observations to these Corot data and published updated ephemeris. And down here we see an example of Corot 1, the first Corot planet detected. We have here basically, this is again an O-C diagram, where the spread of the red lines, which are 2 different models, show the uncertainty predicted from the Corot ephemeris. So the uncertainty was, for example, these are not in years now, but here's TESS, this is 2018 or 2019, it was plus minus 30 minutes. But reobservation showed that they are indeed somewhat later, and here from ETD, the black values, that cohort 1 indeed has later transits at the period that was reported in the original paper somehow had apparently a larger error than they published, which was been quite frequent. And then the test data, which is a red point here, they really fixed this ephemeris very nicely. Again, and down there we see the O-C diagram of a revised ephemeris based mainly on the test observation. Test actually observed it twice. But for these types of observations, the amateur ETD observations by amateurs and by professionals are very useful. And this is important in order to reobserve interesting cases, and of course with like the James Webb or any other large telescope. So in the last part of my talk, I just want to make a quick revision of practical ground-based photometry, how to do it for the needs for this follow-up of space-based missions. And so a question is, you observe a night, you get a stellar field, and here's in the green circle is your supposed target. In this case, it's 5526. This box is roughly the photometric aperture of CoRo. The practical one was always changing slightly, but this was a generic value that was used in the follow-up 30 by 50 arc seconds. And you need to do photometry now. Of course, a nice thing, as I said before, would be you just detect the transit on the target, and this case is closed. But in many cases, this is different. You may not detect it, or you may detect something on any of the nearby stars. So what should you do? First, for photometric references, you should take several stars distributed around the target more or less uniformly, and ideally they should have brightnesses similar to the target. In this example here, which was taken on a wide field imager on a large telescope, this was easy. There are more stars than needed really as photometric references, and you can see them here in the red circles. And then, of course, we should measure also the stars that might be potentially contaminating eclipse and binaries, which are those nearby. So we define another set of apertures, which are all faint stars that can be identified on images around the target. One gets a little bit after a while. We had some experiences how far away we have to really do that. It doesn't make sense to measure very faint one this far away because we know it can't generate the transit signal. So here we used some 15 or so faint stars were revised as well, but they weren't used for the photometric references. So we should measure faint stars within the photometric apertures, and somewhat brighter stars can even be slightly outside because PSF is rather large, but they may still affect the photometric time series from the satellite. So here we had several brighter stars also in here that were like, they were also at the same time, they were reference stars and they were analyzed for the presence of eclipses as well. So I'll show now an example here, which was this candidate that was observed in one of the long runs. It has a transit depth of only 0.1%, and it's a field I've just shown in the previous image. And it was a fairly faint one that maybe was not typical, but that's now the data set I had at hand to play with and to set this up again. That's why we actually used for the follow-up of that one a large telescope, which most of our follow-up was done on smaller ones, 80 centimeters, 1 meter or so. So that was with the wide field camera from the INT. And I'll show that now in a quick run through of not the full tutorial that I did 4 years ago, but just the analysis of the photometric data set, and come up to some points of what should be done in these photometric observations and analysis. So I'll quickly stop the share and flip it to my Stop share and flip to a different screen. I'll get to that one, and I need to share again, and we share this whole desktop now. Okay, you should see now my desktop here. You should see the same image to the left with the stellar field here. And what I've done already, which I'm not showing, is actual photometric extraction, and that can be done with quite a number of programs. It basically comes up with a sorry, that was the wrong window. I got that up before. Is it this one? No. Well, I don't find it now. So I had it prepared. This is how it goes. Emacs. It's basically a large table. File of my recent. Yeah. Okay. Yeah. The photometry basically from the photometric extraction is a large table that generates. You see here to the left the Julian dates. It's the exposure time, the name of the image, and then comes a large set of numbers, which are, I think the first one is the full width half max actually, but then come brightnesses, uncalibrated brightnesses of the target and of all the stars that were used in this extraction, over 30. And also some more indicators in the end, sky brightness, and shifts that happen during the photometric reduction, and I'll show that then later. So we have basically a program that interprets this table. In this case, not a header but a footer with the positions of the target and of all these reference stars and of the faint stars and some other values that are there. Okay, so we interpret basically this table here, and yeah, I have set that up already. So we read that in. We have also a file that has ephemeris, that has more information about this specific candidate, like the transit depth and period, epoch, and so on. What type of instrument was used, and I'll show you now. And this shows up for some reason in the other screen here. We get here. No, let's ignore this for now. We get here the photometric analysis, and basically this is our target here. It varies within 1% roughly, and there we have a set of data that are poorer. Okay. This is another view of the same. We have here an indicator that comes out of the ephemeris. If there when should be the eclipse or the transit. Yeah, so we observe fairly well set around this transit. We show the sum of all the reference stars, the brightness sum together of all the reference stars, and we see that the magnitudes went up, which means they got fainter really. This is here magnitudes in this program. So there were probably some clouds or things like that. This is also something that shows the variation among reference stars, if they varied in some problematic way. One diagnostics that is very useful also is to keep track of the full width half max of the point spread function of the stars. I mean the size of the stellar, the size of the stars in your images. In pixel units. In this case, it was fairly good. It didn't vary much, but we've seen that for some reason they vary sometimes, and then you see also something that might look like a transit. We have here the brightness of the sky, which is being tracked, that stayed very flat. Quite often you see the moon comes up or sets, and then suddenly the sky brightness goes up and down, and you should also look at your final result if you might have just there something that looks like maybe in transit ingress or egress. Then in the next panel, and now it comes up larger, yeah, another diagnostics, which is still a calculated value, the air mass. We also track the shift X and Y, and what that is the individual images in a time series are never perfectly aligned because there are slight tracking errors. So the software aligns the images one against a reference image. The one shown here is actually the reference image, and offsets by a certain number of pixels. That is being tracked here. And suddenly we see, oh, there was something bad in the guiding, and the stars moved all by 10 pixels or so. And you see that as a jump in the end in your final photometry. And that means again that this is likely not a transit that you've seen, but it's an observational effect. And then we see, so we have, for example, here at the very end, there was some jump. And then actually there were more images which I couldn't analyze because the field got lost entirely. So that even happens on a professional instrument like the 2.5 meter INT, at least 10 years ago. And then we have all the reference stars here with their brightness. It's always calibrated against a zero average. And we see these stay fairly stable. They stay around zero. This one is a bit more variation. Of this window here to advance. No, sorry, of that one. Yeah, and it basically cycles through all of these reference stars. Okay. What I also show is here a plot M, which again comes up in this window. This shows the noise of the light curve of the reference stars, of all the stars, including the faint ones, which are Fs here, and the target, versus their brightness. And there's typically some relation here. And we see there are a couple of reference stars that have much larger variation than their brightness is relative to the others. So what I do in my re-reduction, right now we've calculated the target brightness from all the other reference stars. So I remove these 3 reference stars, and I'm not telling you in detail how I do it. No, reference stars, no. Weight 5, I set star 5, and I star 6, the weight to 0. Okay. Now these 3 stars have just been removed basically from the basis from which the differential photometry is being calculated, and we replot it, and it looks much cleaner now than before. There are much less variations here. Still, we don't see anything very indicative, and to remember, we don't expect it really, because that target had a transit of 0.1% depth, and in magnitudes that's 0.001. So that is really something we can't detect here. This is between, yeah, because our noise is about plus minus 0.5% or so. So we can't detect an 0.1% deep transit in this. Also, removing these 3 reference stars, these indicative plots here of the sum of the reference stars got much cleaner now. They vary less. And we can look at the other stars now, and that's where we see something interesting. These haven't changed much. Yeah, they're because they are not really affected from the basis of the reference stars. But what we see now is here that we have here a reference star R6 that has a very deep, nice, looks like really a nice eclipse. It's about 5% deep. Okay. And it does something like that, doesn't show up anywhere in any of the other reference stars. We can cycle through all of them. And that's basically what I wanted to show. In this case here, there was a clear case, let's get out of this, of a nearby star that was an eclipsing binary. If I show it here, frame, zoom 2. That the star actually was R6, which is difficult to see here in this. This is R7 here. It's this star here that had actually an eclipse, and it was. I have to repeat that quickly. How far away was it? R6. Yeah, it was in right ascension declination was 3 arc seconds in right ascension, 15 arc seconds in declination away, and that is within the PSF of Kourou. So that was very apparently the cause of the observed signal in Kourou. One minor issue that's still also to contemplate is the position of the ephemeris. Here we see the predicted transit should have happened there. However, if we look now at this one, you know, it's not as nicely visible because I restarted it and the weighting has been reset, so all stars are weighted. But we can still see this eclipse. It's a bit earlier, and I checked that it's about an hour earlier, and that was within the prediction errors actually. So this is compatible with the ephemeris we had, that it actually showed up an hour earlier. And that is a typical case of a successful finding of a false alarm in ground-based follow-up photometry. And I will go back to the main slides again. Stop share. Go back to that one. Share screen and come to the end. Desktop, PowerPoint. Share. So I think you can see it again. Yes. The requirements for high precision and successful follow-up photometry is, of course, to do everything as good as possible, largest use the biggest telescope you can, but of course, you have always your limits on the side, on the telescope that you have available, on the quality of your mount and also of your CCDs. For amateurs, it's, I think, better to observe only full transits. We have often done also conclusions from partial transits, but one has to be very careful then on the diagnostics we have, that this is real or not. And you have to revise if the timing is really reliable or not. On-off photometry also has been done, and I've become, during the follow-up of Kourou, less and less a fan of it, even if I initially promoted that. That's basically you observe one night during a transit, another night off transit, and you compare the two data sets. But there are often jumps that are just not explainable. For example, you see in your follow-up that it's on target, but it seems to vary much more than what the satellite has seen. And there are often just then factors that there's maybe the moon or the transparency of the atmosphere has changed in some way. So I don't think it's really that reliable for most cases, at least. You should keep the stars on the same CCD pixels. Oh, sorry, this went away. You should get photometry of all nearby stars for a useful set of reference stars, and diagnostics that are needed are these movements of the stars, the brightness of the sky, and the full infrared max. So for the Plato follow-up, also what we have to set up, and this is now things that are being discussed with Günther in particularly uniform ways of reporting, that we have templates for manual reporting and for automatic reporting, that we should attempt to set up a uniform software for the uniform software of analyzing data from, sorry, there's somewhat wrong in the slide here. Uniform software would be nice, at least. And this is something that is being discussed right now for the Plato photometric follow-up. Should we use specifically written routines, or should we use products that are especially common in the amateur community? And something what I'm currently trying to look to learn is AstroImage J, which was really the reason I've rerun my old software packages on this particular target I've just shown, is to learn again, how did this all go? And now, how does AstroImage J compare to what we did? And does it really fulfill our requirements? And maybe there are some other packages that could also be used. We really have to look into that. So that's it for now, what I wanted to show, and any questions are welcome.